Thanks for coming back for another installment of Joe Does Chemistry. In this little video, we're talking about buffer capacity, and this builds really on our last two videos. And so there is the same assumed prior knowledge as the previous two buffer videos. I expect that you know something about Ka and Kb reactions, as well as good old K neutralization. This is still essentially a multiple acid-base mixture. And so we're going to have to deal with having multiple acid-base reactions. And of course, it's still a buffer, and I can still solve it using good old Henderson-Hasselbalch. The issue with buffer capacity is that all buffers have limits. Buffer capacity is defining what the limit is for a buffer to be effectively buffering. And I know you may hate this because it's not exact, right? But buffer capacity is really context dependent. And what I mean by that is if you consider blood, which we mentioned is a buffer, right? Normal blood pH to be a healthy individual must be maintained between a pH value of 7.35 and 7.45. If you're on either side of that range, you are ill. If you have a blood pH below 7.35, you have what's termed acidosis. If you have a blood pH that's above 7.45, you have a condition known as alkalosis. And so the effective range of a blood buffer is really pretty narrow. It's a nominal pH value of 7.40 plus or minus 0.05. Industrial buffers in a chemical setting are far more tolerant. And so the standard sort of industrial rule of thumb is that buffer capacity is a range of plus or minus 1 pH unit from the nominal pH. Again, this is just a rule of thumb. A specific application might allow for a broader range or a narrower range, but this is just kind of the standard. And so if I had a pH 4 buffer, and I'm trying to maintain, therefore, a pH buffer of 4, I consider my solution to still be buffered as long as the pH is somewhere between 3 and 5. Right? 1 pH unit above 4 and 1 pH unit below 4. I can calculate the buffer capacity pretty easily using Henderson-Hasselbalch, and this is really just an extenuation of what we were doing in the previous video, where we talked about adding an external acid or base to see what happened to the buffer. Right? First, I need a buffer, so I mix 250 milliliters of 0.5 molar acetic acid and 500 milliliters of 0.5 molar sodium acetate. Right? The sodium acetate's a salt. The salt, when dissolved in water, dissociates. So it's sodium and acetate is the conjugate base of acetic acid. So it is, in fact, a buffer. And I can calculate the pH using Henderson-Hasselbalch, and then I will, from that, calculate the buffer capacity. So again, good old Henderson-Hasselbalch, because it's just the ratio of concentrations and the volume is the same, allows me to use moles. Right? 0.25 liters of 0.5 molar acetic acid is 0.125 moles of acetic acid, and similarly 0.5 liters of a 0.5 molar sodium acetate solution gives me 0.25 moles of acetate. And good old Henderson-Hasselbalch, right, the pKa, right, is just the negative log of the Ka. And so the pH of this buffer, as made, when I just mix the acetic acid and sodium acetate, is 5.04. If I want the buffer capacity, right, the question is how much acid or how much base could I add, right, to move the pH by 1 pH unit? And the reason this is important is if you consider what Henderson-Hasselbalch is implicitly telling me about pH, right? The pH of the buffer is really solely determined by the ratio of the conjugates. And so if I have 0.25 moles over 0.125 moles, that's a 2-to-1 ratio. Quite frankly, any 2-to-1 ratio will give me exactly the same pH. And so if I were 0.025 over 0.0125, still pH 5.04. Or throw a whole bunch of other zeros in there, right? As long as the ratio ends up being 2 to 1, it's still 5.04. The problem is this bottom buffer has so little acid and so little base in it, I can probably just breathe heavily on it and change the pH. Whereas the top one, because it has much more of the acetic acid and much more of the acetate, would require me to add more acid or more base to it. Okay, and so I have my acetic acid acetate buffer, right? Henderson-Hasselbalch is really the solution to the K equation for this reaction at the top. Given my current acetate acetic acid concentrations, the pH is 5.04, and I consider it to still be buffered as long as the pH stays above 4.04 and below 6.04. And so I can pretty easily calculate how much acid or base it would take to do that using good old Henderson-Hasselbalch. I'll look at the lower limit first. If I'm going to move the pH from 5.04 down, it's because I'm adding acid. And so it doesn't really matter what acid I use, but just so I have a representative acid, let's say I add HCl. I now essentially have a multiple acid base problem like in the previous video. Right? It's really, again, a case of having more than one acid, more than one base, and more than one acid base reaction. But again, if you look back at that previous presentation, we can sort through these by K, and we end up with the same situation as before. I've got a super frickin' big neutralization reaction. That's going to get solved first. That changes the concentration of acetic acid and acetate, which then becomes the second biggest reaction, biggest K reaction that I could do, which is the acetic acid buffer. The HCl is gone after the first reaction, and so I can't actually do that frickin' big third reaction. And so, in the context of an ice chart, the super frickin' big reaction is acetate plus HCl gives acetic acid plus chloride, right? This is a little different than the previous problem because in the previous problem, I knew how much acid I was adding. Here, the question really is how much acid can I add because I already know what the pH is that I'm shooting for, which is 4.04. And so I don't know how much HCl I'm adding. What I do know is what happens when I add HCl. For a little bit of HCl, the HCl is a limiting reactant. It goes to 0, right? And the HCl amount that I added gets subtracted from the acetate because it's turning the acetate into acetic acid. And so my acetate concentration goes down and my acetic acid concentration goes up. And so I can solve this with Henderson-Hasselbalch because, again, I know the target pH is 4.04. And the question really is how much acid, HCl in this case, can I add before my pH gets to 4.04? And so I just need to solve for X. And sadly, trigger warning, there is a log in there. But have no fear, I subtract 4.74 from both sides. That just gives me minus 0.7 and a log on the other side. And of course, to get rid of the log, I use the anti-log, which is 10 to the power of X. And so I essentially raise both sides as powers to 10. That gets rid of the log on the right-hand side, right? And it's just a number on the left-hand side, 0.1995. So I just cross multiply and solve for X. And what I find is for this particular buffer, if I added 0.206 moles of HCl, the pH would have dropped to 4.04. Now, moles is good. In this case, molarity is better because, of course, if I had a bucket of my buffer instead of the original 750 milliliters, it would take more acid to lower the pH. If I had a swimming pool full of my buffer, it would take more moles of acid to change the pH. And so buffer capacity is specified in molarity, which is moles per liter, because then the volume doesn't matter. Right, so in this particular case, 0.206 moles was added to the original 0.75 liter buffer to move the pH. And so the acid buffer capacity would be specified as 0.275 molar. The base buffer capacity would be different. Right? It's the same basic process. I'm now going to add an extraneous base. Let's call it sodium hydroxide. Again, it doesn't matter what it is. In this case now, I end up with a super frickin' big reaction as well, but now it's hydroxide reacting with acetic acid to give me acetate. And so the base essentially does the opposite of what the acid does. It decreases the amount of the acid in the conjugate acid-base pair, and it increases the amount of the base. And so again, it's changing the initial concentrations. And so it's changing the initial concentrations in good old Henderson-Hasselbalch. Again, I'm trying to solve for X. I know my target pH is 6.04. That's where my effective buffering region ends. And so I do what I did before, subtract 4.74 from each side, raise both to the power of 10, cross multiply and solve for X. It actually takes less base than it did acid to shift the pH. Again, I prefer to specify the buffer capacity in molarity so that it doesn't matter what my initial volume was. And so my base buffer capacity is 0.14 molar. Right? And so if I truly want to accurately describe a buffer, I need to specify the nominal pH because, of course, the whole point of a buffer is to hold the pH constant. The pH matters, but it also matters how well it can hold the pH. And that's really what the buffer capacity is telling me. The bigger the capacity, the better the buffer. In this particular case, a full specification of the buffer would be a pH of 4.04 with an acid capacity of 0.275 molar and a base capacity, buffer capacity of 0.14 molar. And so ends our discussion of buffers. Come back to our next video where we'll talk about titration curves.